Yeah. Something buys. Oh, yeah.
All right. Whew. Almost ready. Oh, hang on. And I won't be here on Friday too. I'm going to a conference in North Carolina, and Gary will be teaching mass spec. So anyway, he was going to be teaching. So you're not going to miss me much.
Let's do.
Says who? Okay. Okay. All right. So let's just do some, like usual, some recap. Questions. By the way, I posted the key of the quiz online. Grace done grading them. I'm taking them with me on the plane today so that I will just have a look and then I will return them to you on Monday. Okay. So what are the different species of matter that can be analyzed using spectroscopy? What did you group C do today? No. Well, no, I didn't. You did see that. Didn't mean the question was not for food types. Sorry, it was for the matter. What was the procedure you called? Atomic. So atom or what other form of matter can either be an atom or a molecule. Yeah, that's it. All right, name the different forms of radiation matter interaction. So when light interact with a matter, what do we get? We get either absorption or emission, fluorescence. Very good. So absorption, fluorescence. What else we talked about also with the cheese group today? When we were saying, well, if the flame is cold, what's going to happen to the light? Oh yeah, scattered. You're answering all the correct answers, but not to the question I'm asking. Yeah, so scattering of light, refraction of light, like in refractive index, diffraction of light when the light is broken or divided into different wavelengths. These are all called interactions of light and matter: absorption, emission, scattering, diffraction, refraction. These are kind of interactions. Okay. What are the spectral regions relevant in food analysis? Where did caffeine absorb, in which region? UV. Okay, so now that you know what I'm asking, so what are the relevant regions in food analysis? UV, visible range, and one more? Oh yeah, very good. Thank you. Okay. And then what are some applications you cannot go wrong? Say, name anything. Identification, quantification, structural elucidation, compositional analysis, forensic, all of that. Okay. So we have three types of energy: electronic, vibrational, rotation. So when you hear electronic energy, how do you define it? You remember? It comes from, you hear electron. So when the atom or molecule is in excited state, electronic excited state, what happens to the electron? It jumps to a higher shell, energy shell or valence. This is electronic. It has to do with the electron getting exciting and jumping to different higher shells. When you hear vibration, is it within an atom or within a molecule? Within a molecule, the bonds of the molecule within the atoms in a molecule are always in vibration. And then when you give it IR radiation, it's going to vibrate a little more. Okay. So electronic energy corresponds to UV vis range, UV visible spectral range or region, whereas vibrational energy corresponds to IR region. Okay. So what's the difference between absorption and fluorescence in energy? So when light hits a matter, what happens? If it's in the right range or allowable energy shifts, what's going to happen? The atom or molecule is going to do what? Absorb. Yeah. So it's going to absorb energy. And then it doesn't stay in the excited state, right? It just has to release energy and go back to the ground state. So by doing so, it emits some energy in the light form or heat or heat. Mostly a little bit of heat and some light. That's fluorescence. Emission of light is when the atom or molecule fluoresces. And it's always the energy of fluorescence, always less than the energy of the absorption, because part of the energy is released as heat. That's why the wavelength of the released energy or the emitted energy is always longer than the absorbed energy. The shorter the wavelengths, the higher the energy, so you have more frequency. Shorter wavelength, more frequency of your oscillations, higher energy pockets. Longer wavelength, less energy, less frequency. Okay. And that's, I just explained the last one. Okay, we'll save that for next time. So we're going to talk about atomic absorption. Group C already did that in lab. So now let's reinforce some of the knowledge you learned in the lab and for the other groups to learn about atomic absorption. So, or atomic absorption and emission spectroscopy. So we have absorption, we have emission. So for absorption, AA stands for atomic absorption, S stands for spectroscopy. And then you have the emission. You can also measure emission of atoms. And that's called atomic emission spectroscopy. And then within absorption, you have flame atomic absorption spectroscopy, where Group C did use a flame atomic absorption unit. Or you can have electrothermal atomic absorption spectroscopy. It's not very common. I'll talk about it briefly later. And then in the emission world, there is flame emission, which is very, very old. You don't see those photometers. They call them a photometer with filters rather than chromators, monochromators. Anyway, I'll explain them later. They're not as common anymore, but what's very common, and if you work in an industry where they do a lot of element analysis, you'll see ICP units, inductively coupled plasma atomic emission spectroscopy. It's a mouthful, but I will explain it later. So atomic spectroscopy is generally used for mineral analysis. So in food, we care about mineral nutrients like calcium, iron, sodium, potassium, and the salt. And in soil, for example, they also measure mineral elements in the soil because it has to do with soil health. And then also we care about toxicants like heavy metal. They shouldn't be in food. You shouldn't be exposed to them. So that's where atomic spectroscopy comes in handy to monitor heavy metal in food and water sources and to determine mineral nutrient content for in food for human consumption. So because we're talking about food, I'm not going to talk about soil. It's food analysis. So you all love the periodic table, right? So you all know exactly how things are divided in a periodic table, right? No, I don't even know. It's just been confusing. But anyway, this just to demonstrate that most of the elements can be determined by atomic spectroscopy. And it's very important for human consumption to have in food to have essential nutrients like calcium, phosphorus, potassium, sodium, iron, chloride, manganese, zinc, copper, all of these are essential nutrients. And then we have the toxic elements. We don't want lead or mercury or cadmium or nickel in our food or water. And then USDA database have a lot of foods where all these essential nutrients have been determined. So there are references, USDA references for some foods. Okay. All right. So we already talked about the principle of absorption and emission, and the focus here is electronic energy. Because it is atom, there's no vibration, there's no rotation. These are characteristics of a molecule. So since we are going to determine the absorption or emission of a singular atom in a gaseous form, not ionized, that's what neutral atom means. So that's why it's only electronic energy. So we only measure in UV and visible range, the absorption and emission or emission, where electron goes on to a higher shell. So again, in atomic spectroscopy, only electronic energy. So the same element will have absorption and will have emission range. So element A and element B. You can see that absorption is measured at a shorter wavelength, and the emission of the same element is measured over a lambda max that is longer. Again, emission is always of lower energy, longer wavelength. I'm repeating this multiple times so that you can learn it and remember it. Okay, so the same element can absorb and emit light, but the difference is in wavelength and the energy. So again, the same principle, we have ground state for an atom gets excited, and the difference in the energy from ground state to excited state, the same energy that the light carries, that it absorbs. So we do not have vibration or rotation levels within the allowable energy levels of the atom. We only have electronic energy levels. So the electron, the valence electron, can go from one shell to the other to another within allowable energy levels. There are no rotation or vibrational allowable energy in an atom. Okay, any questions so far? Okay. Now let's talk about what happens in an atomic absorption or emission unit. So what Group C did in the lab today is you start with a sample that usually if it has organic matter, you have to oxidize the organic matter. So you have to get rid of the organic matter, burn it off, oxidize it. Either you burn it off in a muffle furnace at very high temperature, you burn off your organic matter, or you use really highly concentrated corrosive acid where you digest and oxidize all of the organic matter. What remains in the sample is your inorganic matter that has your minerals, not vitamins. Don't confuse minerals and vitamins. Inorganic matter will have your minerals. Okay, so what group C did, they got the crucible that was ashed, meaning all of your organic matter has been incinerated, burned off, and then you had ash, which is the inorganic matter with the minerals. And then they dissolved it in acid to bring the elements into solution and diluted it. So you have a sample, that's why it's in blue. You have an aqueous sample now, acidic aqueous sample with your minerals in solution. So the first step is you put your sample and it goes through a nebulizer. So it gets sucked in a tube into a nebulizer that converts the liquid sample into mist. So now all of your sample is in small, small particulates mist, and this goes into a flame or a plasma. Flame for absorption, plasma for emission. Goes into a flame. What happens during that flame? Your carrier solvent will evaporate. That's the first thing. So you lose your acidic aqueous, will evaporate, and then your minerals are actually in a molecular form. So the heat breaks the bonds. So sodium chloride, calcium phosphate, bonds will be broken. And then you have the atoms now in a gaseous state, but neutral. So you have your solution with your minerals in molecules. They get into the flame, the solvent vaporizes, your molecules get atomized, meaning the bonds break into atoms. Now, we want to prevent ionization. So the flame shouldn't be too hot. If it were too hot, your atoms will ionize. We don't want that because ionized ions will have different absorption spectrum than atoms. So we don't want that. So we want to make sure that the flame is hot enough to atomize, but not to ionize. If your atoms ionizes and you're measuring at lambda max of an atom, neutral atom, you will get underestimation because your ions absorb at different wavelength. Okay, so that's why it's very important to adjust the flame. Okay, so now we have atoms, but now they are in the flame. How are we going to measure absorption of light? We need a light source. So the light source in atomic absorption is usually a hollow cathode lamp. So the hollow cathode lamp has the interior is filled with an inert gas like argon, and then you have an anode that carries a voltage. So it's a voltage source, and then you have a cathode that is made up of the metallic form of the element. So measuring calcium, then the cathode is made up of the metallic form of the calcium. You're measuring iron, and the cathode is made up of the metallic form of iron. So basically, when you have this cathode made up of that particular element, and the anode here is providing the charge, so the light emitted is within the spectra allowable for that element. So if it's iron, the light is in the range, the energy of the light is in the allowable range for iron, or in the allowable range of calcium, depending on the cathode source. So that's the common lamp that is used in atomic absorption. There is another form of a lamp which is less commonly used. It's an electrode-less discharge lamp, is used for volatile elements, but I'm not going to go much into that one. Now, over the years, we had several atomic absorption units retire. So we had a very old one that died. We got another one, died. Now, I don't think I have a picture of the one we have in the lab currently, but they all have similar components. So the components are, if you can see here, we have a nebulizer and a tube. The tube goes into your sample container and it sucks up sample that goes into the nebulizer and then transform the liquid into mist. And this here is your crucible in a sense. You know how you have spectrophotometer crucibles or sample containers, tubes or cuvettes or whatever. This is your sample cuvette in a sense because your mist is going into this compartment and then you ignite a flame. Then you will see a flame coming out of here because you have your air and acetylene to form a flame. And then your mist goes into that flame and get atomized and are ready now the elements to absorb light. So here's the sample compartment. Here's the tube. Here's the nebulizer. And then here where you see a flame. So your sample has now your elements in a molecular form dissolved in the solution. They go up here into the flame. The bonds will break. Solvent will evaporate. And then now you have atoms in the gaseous form that are neutral. Now, this is your lamp that you change based on the atom that you're analyzing, iron, calcium, sodium, etc. And then it gives out the light in the correct energy range. And the atoms in the flame absorb light. And the remainder of the light after absorption, the transmitted light, will go into a detector. And the detector will convert the reading into an absorption that you read in your software. And then now you have absorption that is directly related to concentration. And then you can plot your standard curve by having standards run. And then you follow Beer's law, which I'll talk more about next week. But Beer's law states that absorption is linearly proportional to concentration at a constant wavelength. So this is another illustration to show you that you have your sample now in the flame, you have light projected through the flame, and that cathode is giving you energy levels that are allowable by the element, and you select lambda max. So iron might absorb light at different wavelength, but you select the wavelength at which you have maximum absorption. And that, when you select that wavelength, you read absorption at that particular wavelength using a monochromator. So the light coming after absorption, the transmitted light will hit the grating system. The grating system will diffract the light into multiple wavelengths. And then you select the filter that just brings you the lambda max and into the detector. The detector here is a photomultiplier detector, phototube. Photomultiplier tube detector, the acronyms. Photomultiplier tube detector. So what the multiplier mean is to amplify the signal. So when the light hits cathode, an electron jumps off and it goes to another, what do you call it here? Cathode, anode, something that will amplify the electrons, and it goes from one to the other, and the signal gets amplified. For example, one electron becomes 27 electrons, then you increase the sensitivity of the detector. That's what multiplier means. It's just, it multiplies the signal. You don't have to really know how many dinodes that there are and how many times it gets multiplied, but basically it multiplies the signal so that you increase sensitivity. Questions? You can stop me if you want me to repeat anything. Okay. So this is another form of atomic absorption where you really use a graphite tube, so no flame. Instead of this region for flame, you have a tube with a surface that withstand really, really high temperature. So you put your sample, you drop off your sample on that platform, and then it heats up to really high temperatures, and then it evaporates. So the solvent evaporates, your molecules will break their bonds, and the atom will go into the gaseous state, and everything else is the same. The lamp, the compartments, the detector, everything else is the same. So it's not commonly used because it's expensive, and then you have a very low throughput, mainly because you have to put the drop, and then do the measurements, then open again, put another drop. You'll see in lab next week, if you didn't do AA this week, is that it's much easier with the flame because you just put your sample tube and then just put that little suction tube, and you don't have to open anything in the unit. You just change the tubes of the samples, and it's much faster to a higher throughput. So, but the benefit is you can, if you have limited sample amount, this would work better than flame, because flame, you just have to have at least 10 milliliter because it just sucks the sample very quickly. And then it does have low threshold, so much higher sensitivity than the flame. But it comes with a lot of different, negative things. Okay, I'm going to start flame emission. Okay, flame emission is, instead of measuring absorption, you're measuring emission. So the flame emission spectroscopy, known as flame photometry, like I said, old units, they still exist, but they are not very much used. They basically have all the same compartments, except no lamp is needed. So what happens in flame emission is that the flame is the source of atomization and excitation, meaning you atomize like you do with flame absorption using the flame, but at the same time, the flame excites the atom, allow them to go into an excited state. You don't need a lamp. You don't need a light. The flame itself, instead of the lamp being the excitation source, the flame is the excitation source. So once the sample is in, or the atom is in the excited state, it just needs to go back to ground, and it emits light. So the emitted light, or the fluorescence, reaches the detector, and we measure emission. That's the difference in this case between atomic absorption and emission. It used to be commonly used specifically for sodium and potassium because they have very low excitation energy. So you don't need a lamp, so they can get excited by the energy of the flame. So low excitation energy. So flame emission or flame photometry was commonly used to measure sodium and potassium. And you don't have a monochromator, you have a filter that just filters out the fluorescence wavelength. So very simple equipment. Now we moved away from it, and now we have much more advanced unit. Is the inductively coupled plasma emission spectroscopy. So plasma, which is an ionized gas, is used to atomize and excite. So argon gas is used, and argon gas has high concentrations of cations and electrons. And then we can heat up the gas using radio frequency power when we apply it to copper coil. And then the temperature can be really, really high. And then when the sample goes into the plasma, it gets atomized and excited. So that's the plasma. So the same thing, you have a pump that pumps up the sample from a tube into a nebulizer. You get the mist into the plasma instead of a flame. So you have this radio frequency and applied to copper coil, and then the temperature of the argon gas increases, and then we get ionized gas, which is the plasma, and the sample get atomized, excited, and then they emit light, and the light goes into the detector unit where you have a monochromator or a grating system that will diffract the light into multiple wavelengths. And inside, you either have one photomultiplier tube detector or multiple. So we call that sequential or simultaneous. So your instrument might have one PMT, and you just change the adjustment of the filter to measure emission at, let's say, 500, and then 550, 600 for all the different elements. So if you have multiple elements that you need to measure, you don't have to change lamps anymore. You just change the wavelength of emission and take readings if you have one photomultiplier tube. But some equipment are equipped with 8 photomultiplier tubes, so you can get 8 measurements all at once. That's, we call it simultaneous. Other expensive units have charge injection detector that monitors many, many elements in one go. And I'll explain that in a minute. So this is just a diagram to show you the plasma and how it's ignited. So just FYI. And this is more on the detectors. So sequential, meaning you have at the cheapest, you have a spectrometer with one PMT, and you just change, you dial and change the wavelength sequentially and measure the emission of multiple elements. Or you have up to 8 of them with a diffraction that simultaneously send the light to those 8 different PMT, and then you can get up to 8 measurements all at once for different elements, 8 elements. Or you have the usual, the spectrometer, which is basically a detector that allows you to convert multiple wavelengths into electrical signal and give you the emission of very many elements all at once. We're not going to go into the physics of that. I don't even know the physics of it, but basically you're simultaneously measuring very many wavelengths at the same time, emissions at different wavelengths for a large number of elements. If you're working later on in a lab that we measure multiple elements in food or in soil, you will find this kind of detector there, which saves so much time. Just how you prepare your sample and you determine all the elements very fast. Okay. All right, so now sample prep. So like I said earlier, in lab, you're gonna get your sample already out. So next week we'll have the almonds and we will have the baby cereal. These will be already put in a muffle furnace for you. All the organic matter will be incinerated, and then you have the ash that contains your mineral in organic matter. And then you dissolve it in concentrated acid to bring it back into solution, and you dilute. So later on, there will be a chapter on minerals. We're going to describe wet ashing and what it means. Instead of putting it in an oven at a very high temperature, you digest with concentrated acid. So you can do that, and your minerals will be in solution right away. You don't have to do anything other than dilute your sample. And then we have direct injection. This happens if your sample is an oil sample, for example. You do not need to, or water. So you don't need to ash. So you just dilute, take out the sample right away without ashing. So in the lab, you will be working with reagents, so mostly a concentrated acid. You will be putting some reagents in there, like lanthanum chloride, to break down large polymer of calcium phosphate. So we call it calcium pyrophosphate. So calcium forms like these big molecules with a lot of phosphates interacting. So it's a really large molecule, and it won't go into the flame. It won't stay in solution. It's so big, it might just precipitate out, linger on the plastic or glass of your container, and not make it to the flame. So you will have underestimation of calcium. So we add lanthanum chloride that actually breaks off the phosphate. So the lanthanum will bond with the phosphate, freeing your calcium so that it goes up into the flame and atomize. So that is important for calcium, but it's not important for other minerals like iron, for example. And then we always have to run a blank just in case the HCl we're using or different reagents we're using might have contaminants of the minerals, contamination with iron. So we always have to use a blank and subtract from the absorption of your sample so that we correct for any contamination. Obviously, we need standards, so we can have standard curves and determine the concentration using the equation of the line. And very important for this analysis is that everything we use, all the containers, glassware, volumetric beakers, tubes, everything has to be acid washed. Because if we don't acid wash them, you might have contaminants of minerals on these labware that will cause an overestimation in your sample, because you won't necessarily have the same contamination in the flask you used for the blank compared to the flask you use for the sample. So if the blank will not solve this problem, contamination will be different in the glassware. So that's why everything will be acid washed for you for that lab. acid will solubilize any contaminants and get rid of it. All right, so I briefly talked about this with group C. You got overestimation of your calcium because you might have needed to dilute it a little better or more, because you have to select a concentration or dilute your sample to a concentration where it meets the linear curve of your standard curve. So you will notice that we're going to prepare calcium at different ppm concentration than iron, because you have a linearity is different. So we will prepare standards at 5 different concentration, construct a curve, and make sure our samples are within the linear range so that your equation of the line, the linear equation of the line applies. Otherwise, if your sample concentration is outside of the linearity of your curve, then you will have either over or under estimation. So it's very, very important that we identify the linearity of your standards. Make sure we prepare concentration so that our curve is linear. And then we dilute our samples so that the concentration fits within those standards. And we always work with standards that are very, very pure so that you don't have to worry about interferences. Speaking of interferences, we have something called spectral interferences. So the lambda max of iron and zinc is the same. So if I just want to measure iron and I don't want to measure zinc, I cannot choose lambda max in this case. I will choose another wavelength that I know iron will absorb light, but zinc won't. Even though I will lose some sensitivity, but that's better than measuring both iron and zinc at the same time. Background. So this comes when our flame is not very hot. Your molecules won't break into atoms. So you will get scattering of light and overestimation. The opposite can happen if your flame is too hot, then you can get ionization. And if you get ionization, they won't absorb light. The ions will not absorb light at the same wavelength that the atoms absorb, so we get underestimation. This helps with answering one of your questions in the lab report for atomic absorption. Transport interferences, meaning if you have other components that might absorb light at the same wavelength as your elements of interest, that's why we run blanks. That's why we use the same reagents for blank versus samples to avoid that. And also we prepare the standards in the same reagents. So all the standards that you would prepare would have the same HCl and HCl concentration as your samples. You'll see that in the lab. And then we talked about calcium pyrophosphate and the need to use lanthanum chloride so that we get the calcium into the flame, into the atomic state. And that's the ionization. If we have really hot flame, your atoms will convert to ions, and then they won't absorb at the same wavelength. So we get underestimation. Last here is comparison of atomic absorption and ICP. So ICP is more expensive of an instrument. So if you don't have funding to get ICP, then you would go with atomic absorption, which is fine. It's an older equipment. Everything is like a workhorse. It rarely breaks down, and it just gives you this, good results, except it's not as sensitive as ICP. So if you're looking at those, minor elements or potentially contamination with toxic elements, it's better to use ICP because better sensitivity, lower threshold. And then ICP also does not require lamps, and you don't need to change lamp. You have higher throughput. And then if you have this expensive detector, usual detector, you can monitor many elements at the same time. So pros and cons, but it all boils down to, can you afford having ICP? If you can, go for it. In the future, these is for lab, you already know your assignment. So that's it. Questions. I know a lot of information, but it helps to, you don't have to listen to the entire lecture, the recorded lecture. You can just go to the place that you want to reinforce, but you have questions. Okay, it was very quiet today. I didn't ask you very many questions. Okay. One of those days. All right. Well, thank you. I will see you on Monday, but you have class on Friday. I just won't be here.